Hi, thank you for taking the time to listen to this presentation entitled The Contribution of Body Center of Mass Velocity to Basketball Ball Release Velocity Across Shot Distances. So once a ball leaves the hands, it follows a trajectory, which is governed by the laws of projectile motion. Now, a ball released at the same position relative to the hoop can have more than one trajectory and still result in a successful shot. Ball velocity can be broken into two parts. The velocity that comes from the body center of mass at release, as well as that's left over, which is contributed to the arms. Previous literature suggested that with an increase in shot distance from the hoop, the center of mass vertical velocity increases at release. So with an increase in center of mass velocity at release, does this then reduce the arm's contribution to ball velocity? So what we did in this study was increase shot distance from the hoop, which systematically increased the center of mass vertical velocity at release. What's been known is that the ball velocity at release would increase with the increase in shot distance. And again, the center of mass vertical velocity at release would increase as well. What was unknown is with an increase in center of mass velocity at release, would that then reduce the contribution from the arms? So we collected some data in the gym with 7 recreational players, 4 of which were part of the women's university club team. They shot at least 10 attempts from each of the 3 positions. They started at a quasi-static position on 2 force plates in which they received a chest pass from a person underneath the hoop. And upon receiving, or they were then instructed upon receiving the pass to then shoot as if they were in a game. We used a video camera to track the motion of the basketball, and we used the net impulse equals change in momentum theorem to calculate the center of mass velocity at release. We used horizontal displacement and vertical displacement of the ball from release to the frame of when it just entered the rim and its flight time to then determine the ball velocity at release. So here with this graph, we have the vertical velocity in the unfilled circles, the horizontal velocity in the filled circles. In red, it's a close distance, green is medium distance, and blue is long distance. What our results suggest is that if you have it, you use it. So an increased center mass velocity at release results in an increased contribution of the center mass velocity to ball velocity at release. Now this is true for both the vertical and horizontal components and across all 3 shot distances. This also was seen across all participants. What this is saying is with an increase in center mass velocity at release, it has a greater contribution of center mass velocity to ball velocity at release, thus reducing the contribution required from the arms. So with the increase in contribution coming from the center of mass and decreased from the arms, if that is seen as advantageous, what can we do to achieve a greater center mass velocity at release? Well, one thing would be to generate a greater net impulse during the shot prep. This could afford greater potential for the center mass velocity at release. On the left-hand side, notice the horizontal impulse and its contribution to horizontal ball velocity. It's a nice linear relationship, suggesting that with an increase in net horizontal impulse, you see an increase in its contribution of the center mass horizontal velocity to ball horizontal velocity at release. Yet on the right, it's not so clean and linear. It's a little more dispersed. So why would the horizontal be more linear and the vertical components be not so much? That could be due to time. If we look at the time of the ball release relative to the center mass apex trajectory, we find this nice linear relationship across all distances. So what we see is the ball on the left-hand side of the graph, when the ball is released further from the center mass apex earlier in the jump, the shooter will have a greater contribution of the ball vertical velocity coming from the center mass. Now, if they were to wait until they got closer to the center mass apex, they would then have less of the contribution coming from the center mass vertical velocity. This can be seen using the two participants on the left-hand side as examples. The one in purple released the ball earlier relative to or further from the center mass apex trajectory, which resulted in a higher contribution coming from the center mass vertical velocity. While the participant here in pink released it closer or more near towards the apex center mass, which then resulted in less of its contribution or less of the vertical velocity of the ball coming from the center of mass. Now, if we were to look at a commonly used variable, which is the time of release relative to the end of impulse generation, or also generally known as the rate departure or ground departure, it becomes less clear. There isn't this linear relationship all the way across the board as there was in the slide before. What we can do is highlight two participants that have the exact same or the same contribution coming from the center mass vertical velocity, yet at two very different times. One releasing at 0.058 seconds after end of impulse generation, and the other one releasing at more than double that. When this makes sense, as the time to center mass apex strongly associated with the vertical velocity of the individual, of the object. So, the greater the center mass velocity at release, the greater percent contribution of the center mass velocity to ball velocity at release. Thus, in turn, it reduces the arm's contribution. This was seen across all distances, as well as all participants. We also saw that as the center mass vertical velocity contribution to ball vertical velocity increased, it was due to the ball being released earlier relative to the apex of the body center of mass trajectory. Now, if one were to want to increase the center mass velocity that is potentially available to them at release, they could then increase impulse generated during the shot prep phase. Now, with all that being said, our future directions, we would like to increase our sample size, increase the diversity in the range of shooting skill level of the participants, do more within participant analyses, analyze the center mass trajectory contributions to shooting accuracy, and examine the effects of shooting while being defended. I'd like to thank you for taking the time to listen and for all of those at the USC Biomechanics Lab. Thank you.